This is a test review over note cards 1 through 15. On note card 1, we covered sets of real numbers. There are multiple ways to represent a set. The first pictured here is graphed on a number line. We have an open circle at -3, a closed circle at 2, and a line connecting the numbers. Representing the set with words, we would say the set of real numbers between -3 and 2, including 2. If we were to represent this exact same set in interval notation, we would write it as a parentheses, -3, comma 2, bracket. As you'll remember, parentheses means to exclude a number, and brackets mean to include the number. Whenever we use infinity and negative infinity as a part of our interval notation, we need to make sure we're placing it on the right side as well as using parentheses. If we have negative infinity, it always goes on the left because the lowest number goes on the left. If we use positive infinity, it would go on the right because that is the highest number. If we were to write the same set in set builder notation, we would have a brace, x, a vertical line, which means such that -3 is less than x, which is less than or equal to 2, and then another brace. Finally, if we were to write the same set of numbers as an inequality, we would write it as -3 is less than x, which is less than or equal to 2. As you'll notice, that same inequality is apparent in the set builder notation as well. On note card number 2, we had discussed properties of real numbers. For this test, you'll be needing to know the inverse property of addition and multiplication as well as the distributive property. Let's do an example of each. If you were asked to find the multiplicative inverse as well as the additive inverse of -3/4, your additive inverse or opposite would be 3/4. Your multiplicative inverse or reciprocal would be -4/3. If you were given an equation and asked to identify the property, and the equation was 5, and then in parentheses 4 plus 8, equals 20 plus 40, this would be the distributive property. On note card number 3, we covered square roots. We had the product property and the quotient property. The product property showed us that the value in the radicands can be multiplied and put under one radical. They can also be split apart and placed under two separate radicals. The quotient property showed us if we have a fraction underneath a radical, we can make it into two radicals as long as the numerator has a radical that has the same number that was in the numerator of your fraction, and the denominator has a radical that has the same number for the radicand as the denominator of your fraction. The same works the other direction. When you have two radicals divided by each other, you can combine them and place them under one radical sign as long as you keep the one that's in the numerator of the denominator, and the one that's in the denominator of your fraction. Okay, let's do a sample problem. If we're asked to simplify the square root of 45/80, we can divide both 45 and 80 by 5. The reason I would decide to do it by 5 is because 9 and 16 are both perfect squares. Okay, the square root of 9 and the square root of 16 come out to be 3/4. So if we simplify the square root of 45/80, we get 3/4. Another thing we covered with square roots was that you cannot have a radical in the denominator. When we get rid of that radical, it's called rationalizing the denominator. In our example here, we have the square root of 5 divided by the square root of 3. Typically we would simplify this, however, square root of 5 divided by the square root of 3 is as simplified as we're going to be able to get. So we go to the next step, which is multiplying the numerator and denominator by the radical in the denominator. In this example, the radical in the denominator is a square root of 3. When we multiply the square root of 5 divided by the square root of 3 by the square root of 3 over square root of 3, we get square root of 5 times the square root of 3, which the product property tells us can become the square root of 15. In the denominator, we have the square root of 3 times the square root of 3, which is the square root of 9. Being a perfect square, that now becomes 3. So our final answer is the square root of 15 over 3. On note card number 4, we covered simplifying algebraic expressions. You need to be aware that like terms have the same variables and the same exponents on those variables. You can only combine like terms. When you combine like terms, write down the variable or variables and their exponents and add or subtract the coefficients. PEMDAS is what we use to remember our order of operations. PEMDAS stands for parentheses and grouping symbols, followed by exponents, multiply from left to right, divide from left to right, add from left to right, then subtract from left to right. This is study break number 1. If there was anything that was covered in the first 4 note cards that you would like to listen to again, please rewind at this time. Note card number 5 covered properties of exponents. We have the zero exponent property, which tells us that any non-zero number to the 0 power is going to be 1. The negative exponent property showed us that if we use the reciprocal of a number, the exponent becomes positive. If we have a fraction, we flip over the fraction to make the exponent positive. The product of a power shows us that if we have the same base, that we would add the exponents. So base to the n power times that same base to the n power would be the base number to the m plus n power. The quotient of a power shows that we subtract the exponents when moving them from the denominator into the numerator, or vice versa. The power of a power shows us that if we multiply the exponents, it means that we have them on the inside and the outside of parentheses. The power of a product is if we have 2 numbers being multiplied by each other in parentheses and an exponent on the outside of those parentheses, we can apply that exponent to each of the items on the inside of the parentheses. The power of a quotient shows us that if we have a fraction in parentheses and an exponent on the outside, we can apply that exponent to both the numerator as well as the denominator separately. Okay, let's do an example. For us to simplify -3 to the -2 power times 27 to the 0 power, using the negative exponent property, we know that -3 to the -2 can become 1 over -3 squared. 27 to the 0 power is using the 0 exponent property, which means that that is 1. -1/3 times -1/3 is positive 1/9. So our answer to -3 to the -2 power times 27 to the 0 power would be 1/9. Let's try one a little bit harder. Okay, if we're asked to simplify -3x squared times x cubed y to the 4th power, assuming that these are non-zero variables, -3 squared is 9, x squared is just x squared, x cubed to the 4th becomes x to the 12th because we multiply the number since it's power of a power, and then y to the 4th. We have two that have the same base, so we can use the